A finite automata, or as known as a finite state automata, consists of three main words. So let us explore word by word. Finite means something with a limited number. State is a condition in a particular time. Automata is a machine that functions on its own, following some instructions and rules. Now, combining those words together, give me a definition, which is it is a computing machine that have fixed set of possible states. All right, let's take a real life example, which is the traffic light. If you can see here, I do have a limited number of conditions in a particular time, which is red, green, and yellow. Now, if you notice, those conditions are changed based on a rule or a set of input. So in order to go for the new state, so in order to change the color from red to green, I need to have an input to the current state. And as simple as it is, this is the finite automata. But let's demonstrate the concept in another real-life example. The example is the ballpoint pen. Here is the ballpoint pen. I believe that all of us do come across this machine. Alright, so if you just concentrate on the ballpoint pen, you will find that there is a place we can consider as an input, which is the button at the end. Whenever we press the input or we press the button, what happened? The nib of the pen extends, and here the state change. Now, in order to change the state again, I need to press the button again, then the nib will retract. Now, the finite automata is not about the physical part of the computing machine. It's all about the abstract creation used to model a simple computation. For example, let's say our example in here, which is the ballpoint. To demonstrate this using finite automata, I can just represent the state with the circle, give it a name, and then place an arrows, which means that an input here comes and change the state from 0 to 1, and again another input comes and change the state from 1 to 0. And here is basically what do we mean by a finite automata. Alright, moving to our next concept, which is a regular language. Before we just understand a regular language, we will come across a number of symbols and vocabulary that represent the language. Then we will see what do you mean by a regular language. Now we represent a language using something called sigma. Sigma donate an alphabet, and this is sigma. Yeah, okay. Now sigma can be represented in different ways. So I can have like sigma plus to denote a set of all non-empty string on sigma. Okay, so all non-empty string of sigma is equal to sigma plus, while the empty string can be represented using lambda. So lambda obviously is not an element of sigma plus. Now let's suppose I have W, which has a number of alphabet from 1 to K, and all of these are an element of sigma star. Now the length of the string is, here we go, is this number in here. So the length of W is basically the number of an element in W, which is K. So let sigma be an alphabet. Any subset of sigma star can be called as a language on sigma. All right. Now let's check this vocabulary, which is concatenation. Concatenation is whenever I have two alphabet, two string, two set, two languages on a sigma star. Concatenation means when I put them together. So if one of them are an empty set, which is lambda, then the concatenation will be equals to the first set, the set with an element. While if they have alphabet, which is U here, have A1, A2 until AK, V with B1, B2 until BR, then UV, which is the concatenation of U and V, is equals to all the elements of U combined with all the elements of B. All right. Now here definition of a concatenation. Whenever I have two sets and they are a language on sigma, so x, y equals to all the uv, which is the combination of the elements from x and the elements from y. Can I have a concatenation of the same value of the same set? Yes, of course. So here we have the concatenation of x with itself. If we have x0, then we means lambda. If there is xn, then x and the elements of x and the element of x and minus 1. Okay. Now here is an example. Our sigma is A, B, C. Alright? Then I have X, which is a language on sigma, which is AAAB. Y as a language on sigma that has A, CA, and lambda, which is an empty set. Then XY, the concatenation between X and Y, is the first element of X combined with the first element of Y, which give me this A. Then I take again the first element of X, combine it with the second element of Y, which is AACA. Then finally AA with lambda, and it gives me the same AA. And we do the rest for AB. Alright, y to the power 0 is lambda, as we said earlier. Then y square equals when the same elements at the first and then in a relation with itself. So AA, ACA, A with lambda, then CA with A, CA with A, CA with lambda, and finally lambda. All right. This can be represented again whenever you have a concatenation between a set and itself. We can use the lean star. So here, let's suppose I have a lambda with A and B. Consider the language that we have is BB. So we have a single string BB on sigma. Now L star will equals to L0 union L1 union L2, where we do stop infinite. So here for all elements, W is an element of lambda star. W contains only B's and the length of W is even. Alright? Okay. Now moving to our last vocabulary in a language is palindrome. And when I said a palindrome, that means I can read the string the same, going right to left and left to right. For example, here I have this string. If you read it from left to right, we will have as AB, CA, CB, A. If we go from right to left, then it will be AB, CA, CB, A, which is the same. So we just call the string as a palindrome. However, here we have another string, which is CA, CA, BC. If we take it from left to right, as I read it now, if we take it in the backward, then it won't be the same. So we call this as a not palindrome. Now, regularly, as we mentioned here, as you see here, a language is a number of alphabet that will goes inside a finite machine as an input. So we call those language a regular language if and only if a finite machine recognizes it. And now, after two slides, we will see how a finite state machine can recognize a language. Now, the types of our finite automata can be divided into main categories. First category is the states or the machines that does not have an output, such as deterministic finite automata and non-deterministic finite automata. And we have the second type of a machine, which is that has an output like the finite state machine. And in our lecture today, we will discuss the Mealy state machine. How we can represent those types? Either we use the transition table, and we will see what do we mean by transition table in depth once we go to the types, and using a transition diagram. So here is the end of part 1. We just introduced the finite automata, which is a computing machine that accepts an input and go along these states. Languages, which is a number of alphabet that come across a machine. And finally, we saw a brief type of finite state machine and its representation. Hope everything is clear, and let's go for our part 2.